Okay, so hi everyone. Welcome to our weekly seminar here at IA4th. Today's speaker is Alessandro Paggi, who is going to give us a talk about blazars, beams, and beyond. But before, let me introduce quickly Alessandro. So Dr. Paggi got his PhD in astronomy in 2010 at the University of Rome Tor Vergata, with a thesis titled Flares in Blazars, under the supervisions of Professors Bagnetti and Cavaliere. Then during the PhD, he worked on data analysis and modelization of multi-wavelength emission from blazars. And he visited the Harvard-Smithsonian Center for Astrophysics, the CFA, in US to work on X-ray spectral analysis of blazars under the supervisions of Dr. Dan Harris. Then in 2011, he started working as a postdoc fellow at CFA under the supervision of Dr. Fabiano and Dr. Kim, focusing on nuclear and diffuse X-ray emission from agents and galaxies and developing pipelines for spectral and imaging analysis. Then in 2017, he moved back to Italy at the Università di Torino and at the Astrophysical Observatory of Turin, to work on multi-wavelength emission and the large-scale environment of agents under the supervision of Professor Massaro and Raiteri. And now is currently working at the University of Turin on X-ray polarization from blazars under the supervision of Professor Massaro. Okay, so without any further ado, the floor is yours, Alessandro.
Okay. Thanks, Caroline.
Alessandro, you are muted. Alessandro.
Sì, Valentina,
Alessandro,
one second.
Okay. I think you can hear me now. Okay, perfect. So let's start again. Thanks, Carolina, for the introduction, and thanks everybody for being here. In this talk, I will present you some works that I've done on the multi-wavelength selection and characterization of jetted AGNs. Jesus. First of all, very briefly, probably everybody knows, but a brief introduction about blazars. Blazars are radio loud AGNs whose emission extend across the whole electromagnetic spectrum. They are characterized by high and variable polarization, apparent superluminal motion, high luminosities, and their emission is characterized by intense and rapid variability coupled with a flat radio spectrum. All these observable observational properties are interpreted as the result of the AGN jet being closely aligned with our line of sight within a few degrees. These sources are particularly important for the gamma ray sky because they dominate the gamma ray sky. As a matter of fact, they represent about 75% of the extragalactic sources, with this percentage increasing to about 95% when we restrict to associated gamma ray sources, and they also represent about 75% of the extragalactic TeV sources detected at TeV energies. Usually, blazars are divided into big main subclasses: BLX and flat spectrum radio quasars. BLX are the less luminous class with optical spectra characterized by weak or completely absent emission lines with equivalent width smaller than 5 angstroms. Then broadband emission is interpreted as purely non-thermal. They also are found at lower redshift with respect to the other class, the flat spectrum radio quasars, that are more luminous and with the optical spectra characterized by broad quasar-like emission lines, with a bit larger than 5 angstrom. They also feature, together with the non-thermal emission of the BLX, signs of thermal emission in the form of the big blue bump, usually connected with the accretion disk emission. And they also find that larger redshift with respect to the BLX, but recently gamma ray BLX have been found at redshift up to 0.5 and in a case also 3.6. Of course, there can be some selection effects in the redshift estimate of BLX, since they have very weak lines. So the redshift estimate it's particularly tricky. This is the broadband average SCPs spectral energy distribution in the nu representation of the BLX indicated in blue and the transpector radio quasar indicated in red for different observational energies. In general, their LCD, BLX and transpector radio quasar is composed by two main components. The lower energy one is interpreted as the result of synchrotron emission from the relativistic electrons in the jet, while the higher bump is interpreted in BLX mainly as the result of synchronous and Compton emission from the same electrons in the jet, while in fast spectral radio quasar, apart from the big blue bump, the accretion disk emission, the high energy bump is interpreted as inverse Compton from external photons. That is seed photons coming from sources that are external to the jet, like the broadline region, the accretion disk, the dusty domes, and so on. Blazars are also important as multi-messenger sources because they can be the sources for extragalactic neutrinos, as the 2018 extragalactic neutrino detection by IceCube has been associated with flaring blazars detected by Fermi and MAGIC. It's important to have catalogs of blazars as complete as possible because they, as we will see in a minute, they are important for a number of scientific topics. The most used and probably most complete blazar catalog is the Roma BZCAT catalog, which lists more than 3,500 sources, all identified and classified by means of available optical spectra. It also contains multi-wavelength information ranging from radio to gamma ray energies. And the sources in this catalog are usually classified in this way. There are about 1,000 BLX, so-called BZBs, like BLX and BLX candidates. About 2,000 BZQs that are spectral radio quasar, about 200 BZUs that are blazar of uncertain type, and 270 BZGs that are possible BLX with a dominant galactic emission. As I was saying, it's important to expand our current knowledge of blazars, in particular, to expand the catalogs of non-blazars, because about 1/3 of the gamma ray sources listed in the last Fermi catalog for FGL are not yet associated with lower energy counterparts, and so they are classified as unidentified gamma ray sources. That are important because they could be dark matter galactic, dark matter halo that can produce gamma ray emission through annihilation. As a matter of fact, comparing the result of these simulations with the and the expected distribution that comes out from the simulation of the dark matter halos with the number of UGS, it's possible to put severe constraints on the dark matter annihilation cross section. So it's important to reduce as much as possible the number of unidentified gamma ray sources that we have in the catalogs, possibly associating them with blazars. well-known way of selecting blazars is through their mid-infrared emission, in particular making use of the I cannot get rid of this thing.
You read the message.
I have to open the chat. Can you hear me? Can you hear me? Yes. Okay. Okay. Nice. So I was saying, well-known way of selecting blazar candidates is through their mid-infrared emission detected by the WISE satellite, because gamma-ray blazars occupy in this three-dimensional color space a very distinctive region called the blazar locus. So if we have an identified WISE source, we can classify it as a candidate blazars on the basis of its compatibility with its position in this space with respect to the locus occupied by the non-blazars. However, more than 90% of the WISE sources lack the detection of 22 microns in the fourth W4 WISE band, and so it is not possible to apply this method to classify these sources. So we need additional information.
All the red and the blue.
Okay, blue usually in this talk, blue are the LAX, red are flat spectral radio quasar, and purple are intermediate transitional objects that lies in between the region occupied in the space by a flat spectral radio quasar and the LAX. So they can be both.
And you use the two different planes to identify them?
Actually, you can do this, as I will show you in a bit, or you can directly look at the position in the three-dimensional space, or you can do some kind of projection with the principal component analysis and stuff like this. But essentially, yes, you look at the position on the two or three projections. So, as I was saying, since we need, in addition to WISE mid-infrared colors, other information, a possible way to classify candidate blazars is to look at their X-ray emission, since blazars are known to be strong X-ray emitters. So, to this end, I analyzed all the available Swift XRT data images for about 200 Fermi identified gamma ray sources, and merged all the observation from the same source together to reach lower flux, and so pick up fainter sources. And in this in the left panel, you can see this is the field of UGS. The green ellipsis is the Fermi-Lat uncertainty ellipse, and so we looked at all the detected X-ray sources that we found in this Swift XRT data falling inside this 90% uncertainty ellipse. For example, in this case, we find two sources. One is much brighter than the other. On the right panel, you can see the same, this inset zoomed in as imaged by UVOT, ultraviolet optical monitoring monitor of the telescope of on the Swift satellite, and those are the two sources. Those are the X-ray contours, and the smaller inset is the same image, the same region of the sky as imaged by WISE in the 3.5 micron. So we looked at all the sources, X-ray sources detected in this way, falling inside the Fermi-Lat uncertainty ellipses, and we found X-ray counterparts to about 70% of the sample of 200 UGSs. We also looked at the multi-wavelength SCP of all these sources, collecting data from different telescopes. Some of them look like blazars. They have at least 2 amps. In some cases, you can see probably also the big blue bump. And in order to classify among all the sources that we found in the X-rays, those that are compatible, that are possible gamma ray blazer candidate, we use the kernel density estimate technique to find the region where 90% of the known gamma ray blazers fall in this projection of the wise color space. So those are all the sources, the crosses are all the X-ray sources that we found, and we selected as gamma ray blazer candidates those that are compatible with the 90% contours of the known gamma ray blazers in this color projection. In this way, we were able to find 37 gamma ray blazer-like X-ray sources for 33 identified gamma ray sources. As a matter of fact, 29 UGSs feature a unique X-ray candidate, while 4 have a double X-ray candidate. The important thing is that in this way, we don't always select the brightest X-ray source. For example, this is an example of the field of an UGS as mapped by Swift XRT. We find several sources. This is an example of 3 sources that zoomed in. This is the brightest of the field. This is the one that should have been selected with wise colors, because it features the 3 wise colors. And this is the one, this one down here, that we select with the kernel density estimate plus X-ray selection method. So they are not equivalent. They sometimes pick up different sources. So they are complementary in a way. Of course, the key tool to firmly identifying the blazer nature of a source is optical spectroscopy. So to this end, we started a campaign of optical spectroscopic observation using different telescopes like MMT, KIT-Peak, SOAR, Gemini, and so on, and collected several more than 100 spectra, and classified them, confirming or not them as blazers. In particular, for this analysis, 24 out of 33 of these gamma ray blazer candidates were confirmed as blazers, and 12 of them were the same, ended up being the same counterpart selected with the kernel density estimation plus X-ray method. Another important thing to consider about the current blazers catalog is the lack of sources at low galactic latitude. This is the BZGAT, the blazer, the 5th BZGAT catalog. As you can see, it lacks a lot of sources at low galactic latitude. This is due to the fact that at low galactic latitude it's more difficult to obtain optical spectroscopic observation of good enough quality to establish their nature, due to obscuration and other problems that the galaxy plane provides. In order to find possible counterpart to unidentified gamma ray sources or high energy neutrino emission or ultra high energy cosmic rays, it's important to have blazer candidates that are as complete as possible and cover the sky as much as possible. To this end, yes, I built a new blazer candidate catalog, starting from the ALMA calibrator catalog called ACC that lists more than 3,000 bright compact radio sources with, of course, ALMA flux density measurement, and also measurement of the radio slope between 1 and 5 gigahertz. About 3,000 of them are listed in this paper as Blazar candidate due to their flat radio spectrum and also evidence of variability, gamma ray emission, and so on. This starting catalog, the ACC, as you can see, covers the blue dots are the sources from the ACC, the ALMA calibrator catalog, and the red ones are the one from the BZCAT. So as you can see, the ALMA calibrator catalog covers the sky much more uniformly, especially at lower galactic latitude. As you can see also from this histogram, the BZCAT has a dip at low galactic latitude, while the ACC it's more uniform. Okay. Comparing, cross-matching this catalog with the BZCAT, we found that the sources that are in common are much more, are significantly more bright in the, the sources that are in common, yes, are brighter than the one that are not in common. So the ALMA catalog, calibration catalog represents the brightest end of the Blazar population due to the limiting flux of the survey. This is the composition of this ALMA calibrator catalog in terms of literature classification. We see that the main contributors are sources classified as generic radio sources, then there are QSOs, a bit of Blazars, a bit of Blazars, generic AGNs, a little bit of generic radio galaxies, and a little bit of source with no classification, no type. We excluded from our analysis all the other sources that are classified as galaxies, galaxy clusters, stars, etc. And so we came out with the final catalog of 1,580 sources that we call the ALMA Blazar candidate, or ABC. This is the redshift distribution of the BZCAT and the ABC. As we can see, as we said before, the BZCAT extends up to 5.5 in redshift with spectral radio quasar, while the ABC sources with no redshift extend up to 3.5. Also, since we are extending to lower galactic latitude, we also have larger optical absorption, of course. Comparing with this ABC catalog with the fourth Fermi catalog, we find about 260 sources in common. And the interesting thing is that no source in the ABC is classified as a UGS in the for FGL. We also compared with the third Isington peak Blazar catalog, which is a catalog of blazars with the first peak lying at frequency larger than 10 to the 15 hertz, selected with multi-wavelength analysis, and we find only 9 sources in common. We cross-matched all these sources with Gaia that there is to catalog, finding about 800 sources in common, and we find that ABC sources and we also cross-match the BZCAT sources to compare, and we found that the ABC sources are generally less bright than the BZCAT sources, although they span similar ranges in magnitude. And also ABC sources tend to be redder in these colors with respect to the BZCAT one. We also cross-matched both the ABC and the BZCAT with 12th release of the Sloan digital scale survey, finding that ABC sources tend to be bluer than the BZCAT sources, although with low significance. In the Sloan color plane, Butler and Bloom in 2011 found 3 regions to select low, intermediate, and high redshift quasars. And we see that if we plot BZCAT sources on this plane, we find that most of the flat spectrum radio quasar and BLX fall in the low quasar, low redshift quasar regions, while the BZGs leak out, and the same more or less is true for the ABC. Most of the sources classified as BLX and QSO tend to fall in the low redshift phase region. We also compared the BZGAT and resources WISE using the WISE counterparts, finding 1,300 matches, and we see that they have similar W1 minus W2 color with respect to the BZGAT sources, while they appear bluer in the other two color projections with higher significance. We also looked at the, as I said before, X-ray data for this catalog, because X-ray is always important for blazars. Looking up in the Swift, XRT, Chandra, ACES, and XMM Newton EPIC catalog of observations, and we found data available for 170 sources, and we found we were able to extract some 140 spectra for 92 sources. The majority of them are, of course, as we expect, power law-like, if we talk about blazars, but there are 31 that are a little bit more complex, cannot be fitted with simple power law spectra, and require a little bit more work. So probably these are not blazars, so there is some kind of contamination from nearby sources. And we estimated the fluxes for all these X-ray fluxes for all these sources, either through the spectra or through the count rates, if the spectra were not available, assuming a typical slope of 1.8. These are the comparison of the BZGAT and the ABC sources, BZGAT on top, ABC on the bottom, for the X-ray flux, and we see that for different classes of sources, and we see that ABC sources appear to be dimmer in X-rays when compared to BZGAT sources. So in X-rays, we are looking at the dimmer, the lower end of the flux distribution. While looking at the slopes, we find that the average slope of the ABC sources in X-rays is similar to the one of BZGAT. It's only significantly different from the BZP or BLX subpopulation. We did the same thing in the gamma rays, finding that ABC sources appear to be dimmer in terms of flux with respect to the BZGAT sources in gamma rays, and they also appear to be softer in the gamma rays, with the gamma ray slopes of their spectra similar to the one of the BZUs that are blazer of uncertain type.
May I ask, why do you use flux instead of luminosity?
Because the redshift is not available for all of them.
Doesn't this create a bit of a problem?
It could be. That's why also subdivided in BLX and transfer regressive because of their redshift gap. But since we don't have a redshift available for all of them, we wouldn't. Okay, I was thinking about doing this after I submitted. I was thinking about introducing this plot in the second review, but this is the first time in my life that the referee accepted the paper at the first round, so I didn't have any other plot.
So, may I ask us something relevant? So, are these NH corrected or not?
Yes, they are. These are intrinsic.
Okay.
Also,
it's got a higher NH. So.
Yeah. They are corrected by NH are intrinsic flux. Also, I forgot to say it, but also when we look at WISE, Sloan, and Gaia colors, those are all absorption correct.
Okay.
Okay, so finally we use the WISE color to classify these sources, but not in the directly in the 3D space, but by means of the two projections separately. So we drew the kernel density estimate 90% confidence levels for different classes of sources, that is BCB, BCQ, and BCUs in the BCGs for the BCGAT sources, and then we looked at the where the LBC sources fall in this plane, and through their compatibility with this line, we were able to classify about 700 gamma ray blazars candidates of different classes. We also looked at the optical spectral classification of these sources available in Sloan and Lamos release 5, finding more than 100 optical spectra, and we see that the majority of the sources, about 100, are optically classified as QSO, while 12 are classified as galaxies. And most spectroscopically classified QSO classified sources, we classify them by means of their white colors as BCQ, that is from spectral radio quasar, or mixed source, that is in between the DLX and the spectral radio quasars. While the 12 sources are classified as galaxy, we classify them either as BZB, BZU, and in one case as BZGs. There is also a source that has a redshift of 2.6 that is classified as galaxy as by means of its optical spectrum, and we classify it as BZB. As a matter of fact, it has an equivalent width, maximum equivalent width of the lines in the optical spectrum smaller than 1 angstrom. Okay, this is what I just said. This is the link for the catalog if you want to take a look at it. And then another thing that I'm doing right now, it's try to look for extended emission surrounding BLX in X-rays. This is interesting because the presence of diffuse emission surrounding X-ray in X-rays surrounding BLX could be the indication of the presence of intercluster medium that is connected with a cluster, of course. And so this could be an interesting way to study the large-scale environment of this source, and then possibly find a way to estimate the redshift if it's not available, if it's not possible through optical spectroscopy. So we looked at all the PLX in the ZGAT with no redshift for now, and then we will move to the one without redshift. All the sources of this kind in the ZGAT that are covered by Chandra observation. Why Chandra? Because we need high angular resolution observation in order to assess the presence of this extended emission. So we have 48 observations. Not all of them are listed here. This circle here represents the size of the VSF, 90%, and circle the energy fraction of the VSF at the off-axis angle of the source. This is important because Chandra VSF is very sensitive to the off-axis angle, and so it can become much broader as we move to larger off-axis angle. And we also took care of the pileup, the redout streaks, the presence of jets that you can see in the X-rays, as I was saying, also the PSF broadening with off-axis angle, and we simulated PSF for all these sources, running 1,000 simulations for each sources to have an average PSF. And those are the surface flux profiles for these sources, fitted with only the PSF and the PSF profile and the background level. Most of them, as we can see, are just well described by the single PSF, so they are on point light. They do not show extended emission. Of course, some of them are narrower PSF, some are broader, depending on the off-axis angle. But for some of them, we find that the PSF itself is not enough to fit them. For example, look at this or this. There is the presence of an significant extended emission that we model as with a standard beta model that is usually used to represent, to describe the surface density, surface brightness profile of the gas, relaxed gas surrounding galaxies cluster. We also looked for possible bias in this observation regarding the redshift, the axis angle, and the exposure time. We didn't find any obvious bias between the source, the observation that shows extension or point-like source. Those are the residual significance with respect to a fit with a single PSF. The green boxes are the readout streak or the regions that we exclude from our analysis due to obvious extended emission. The yellow circles are the circles beyond which the contribution of the PSF component is smaller than 1%. So those are outside that. We think that the extended emission is dominant. We performed spectral extraction, spectral analysis, X-ray spectral analysis in these regions, finding this temperature. Since we fit the profiles with a beta model, we also can estimate the beta, and through the relation between the galaxy velocity distribution and the temperature published by Wilson et al. in 2016, it is possible to find a relation that from the observed beta gives us the temperature of the gas. Those are the temperature obtained this way. The errors are very big since the statistics is not that good, but we can see that apart a couple of sources, the temperature estimated in two ways are more or less compatible. And also I looked up the distribution of galaxy neighbors that are sources in the field of this BLX that are similar redshift, that can be the indication of the presence of a cluster. This is Macquarie 501 among them. This only has 3, but for these 2 we find several sources with similar redshift to the central BLX that probably belong to the same group or cluster. A similar thing can be done with the radio galaxies that are considered the parent population of BLX, but when we see the jets sideways instead of looking directly down the jet. X-ray emission on these sources on scales of 100 kiloparsecs is well known and can be ascribed to several mechanisms, like single set Compton that is expected to dominate in the hotspots. ICCMB, that is inverse Compton on the cosmic microwave background, when the X-ray emission is generally aligned with the radio axis. Inverse Compton from infrared photons in star-path galaxies, galactic starburst, or thermal emission when the source is hosted in a cluster that arises from the IGF. Okay, so to look for this feature, in 2017 we started a campaign, the snapshot campaign of the channel snapshot campaign, to observe the whole third Cambridge catalog. Okay, we found several extended emission, X-ray connected with lobes, knots, and this kind of stuff. And now we just started with another radio catalog, that is the second Bologna catalog, that lists more than 10,000 sources, and it covers a wide range of redshift and radio powers, and is also augmented by a vast suite of multi-wavelength observation, both in the radio and other wavelengths. And so it represents an ideal sample to investigate the properties of the active galaxies. To cover this catalog, we in 2018 submitted a white paper for the Chandragul target program, that is observation performed when the telescope is cooling down, is not pointing at sources. It has to point at other position in the sky where it can cool down, but in the meantime can also perform observations. And so we requested around 1,000 B2 sources with an exposure of about 15-16 kiloseconds, with the goals of investigating the X-ray emission around this source to look for the presence of X-ray nuclear emission, diffuse emission, and the interaction of the AGN with the surrounding medium to investigate also the feedback processes. Last week we got the 31st observation. Yes, 31st observation. And for the sources we have available data now, we found significant nuclear emission in 25 out of the 31. We also have radio observation at different wavelength coming from VLA, TGSS, LOFAR, and other radio surveys. Those are the results of the spectral analysis of these nuclei. We find for some sources regular, let's say, slopes around 1.8, 1.9. Some are significantly softer. This is because they also show significant intrinsic absorption. And so for these sources, we fixed the slope of the power law in the fit to 1.8 and evaluated the intrinsic absorption. One of the sources, you can see, is significantly piled up with a pileup fraction about 20%. We also found extended emission in 5 of these sources in the same way, comparing the surface brightness profile with of the source of the data with the one from ABSF. Estimated the temperature for 3 of the sources that have enough counts to perform a reliable X-ray spectral analysis. We did it in 2 ways. On the 360 sector and excluding the regions of where we see the radio structure, because these can contribute with some kind of non-thermal emission we said before, and compared this with known cluster and groups temperature versus luminosity in this plane. Those are the 2 sources with known redshift for which we can estimate the X-ray luminosity. The empty and the full symbols are the one for the full symbol is on the 360 sector, and the empty one is on the sector that exclude the radio emission. The temperature are more or less compatible. In this case, we can only put a lower limit. So we can see that for this source 700742, it's more or less compatible in both cases with the group of or cluster ICM emission. While for this source we are a little bit lower. That is, if this source belongs to a cluster in terms of temperature, it's less luminous. Instead, if it belongs to a group, it is much hotter than we expect for group emission. The other source, this situation, this deviance from the expected trend can be due to its highly disturbed structure. As a matter of fact, if we look at it in LOFAR and VLA data, and also in the X-rays on the background, we can see that this source has a wide angle tail of bath structure. That is the jet bends. The origin of the structure is still debated, but it's probably related with sloshing in the ICM as a result of galaxy emergence. As a matter of fact, also the X-ray emission appears quite intense and disturbed. In particular, we found at least 2 possible cavities with not very high significance, 2 sigma for this one and 4 sigma for this one, for sigma significance. But still, this can be an indication of the status of the ICM being disturbed as a result of a recent galaxy merger. The other source, 742, also for this one, I looked for neighbors, cosmological neighbors, sources with similar redshift. I found 1, 2, 3, 4, 5. I guess five sources nearby in the field of this galaxy with similar redshift. Probably an indication of the presence of a small group. Do I still have time? Yeah?
Yes.
Okay, so to conclude, I will show you the result of one of these radio galaxy that has enough counts to perform a more detailed spectral analysis and imaging analysis. That is 3C187. It's at a redshift of 0.465. It's an F2 galaxy, and in the literature, it has been listed as to learn just with this sentence in this paper of 1995 to lie in a rich cluster with 30 members projected between the radio lobes. That's all I could find about the cluster description of this source. But the presence of this source of a cluster harboring this source is still debated. As a matter of fact, if we look at the radio and X-ray data shown here, this is a Chandra image, this is a VLA image, we can see that there is an extended emission in X-rays more or less aligned with the radio jet, with the radio structure. That can be an indication, as we did before, of the presence of ICCMB emission, so non-thermal emission. So extracted the X-ray spectra and profiles in the lobes and in the north and south lobe and in the cross-cone direction. We see that the profiles, the surface brightness profiles in the north and in the south direction deviates from a simple beta model, and they have significant residual significant deviation, especially in the north direction, that may indicate that the X-ray emission in this region is augmented, or at least as a significant contribution from a non-thermal component that can be ICCMB. So we perform a spectral fit in the north and the south lobe. The dotted line, so we perform this fit with a model with 2 components, thermal and non-thermal, in the form of power law. And we see that in both cases, the thermal component appears to be subdominant with respect to the non-thermal one, that is the dashed lines, especially in the southern lobe. And we also compared the property of the spectral properties in the radio and in the X-rays in these 2 regions, the 2 radio lobes, because in the ICCMB scenario, we expect the slope of the spectrum to be the same if the frequency of the synchronous emission is about of the order of the megahertz, and the inverse Compton emission that we look at is around 1 kb, which is more or less the range that we cover with Chandra for a magnetic field of around 10 Gauss. This is a broadband SCD, a simulation of a broadband SCD for the synchrotron and the ICCMB component. Those are the GMRT and VLA data for the north and south lobe. Those are the fit to the 2 available frequency that we have in the radio, and this is the prediction that we infer with the ICCMB model in the X-rays, and we see that even though the errors on the slope of the non-thermal component in the field that I showed you before are quite big, still it looks like they are compilable. So there is the possibility for this emission to be non-thermal in origin. Okay, I will go super fast through this. I looked with the red sequence technique for possible groups or cluster companions for this source, looking at the color magnitude planes of pastels for the sources in the field. The green one are the ones that are not selected as cluster candidate or group candidate, while the red one are the one selected as such. And these are the red circles are the one that we select as cluster candidate, while the green one are the field source that should not belong to the cluster or group. And we requested spectroscopic observation for these sources to find out the redshift and see if they are compatible with the central source. The sources with the cross are the one that we were able to observe at Victor Blanco. The observation, the sky that night was horrible, so we were able only to observe source not belonging to that we select as not belonging to the cluster that are the brightest. All of them resulted as either galactic or other kind of sources, so not belonging to the cluster at all. The only one that we select as a cluster candidate that we can observe is this one, and as a matter of fact, it turned out to have the same redshift of the source. Of course, we have to apply for other nights for this source. Also, I also applied for additional X-ray time for this source to firmly constrain these results. Okay, so to wrap up, we need the Blazar catalogs as complete as possible to provide counterparts to unassociated gamma ray sources that are important for dark matter, and the sources of high energy neutrinos and ultra high energy cosmic rays. And in this regard, multi-wavelength observation are essential, as I show you, to select bona fide Blazar candidates. The high angular resolution in the X-rays of Chandra is very useful to reveal extended emission around blazars and radio galaxies, radio sources, to allowing us to perform detailed studies of its properties, its structure, and the feedback processes that may take place in these sources. And also, the X-ray spectral analysis is very important to disentangle between the different emission processes that can arise in radio galaxies, like, for example, ICCMB, thermal, synchronous quantum, and so on. Okay, I'm done. Thank you for your attention.
Thanks, Alessandro, very much. Let's see if there is. Okay, don't see so far any question here from online participants. So anyone here who wants to ask some question?
Two questions.
Infrared, you mean why?
Actually, let's start with the second question. Okay. So when you are measuring properties of the cluster, I guess you remove the Blazar. Yes. So, but there is evolution. There is evolution of the temperature
Yes. So
the central part of the cluster, the other cluster, there is a polygon. There is.
I totally agree, but the statistics for these sources is not enough to perform such detailed spectral analysis.
Okay, so what I was getting at is that probably the differences that you are getting in the luminosity temperature relation, or between the temperature that you measure in the spectrum and the one that you infer from the data profile, might not be that surprising.
Okay.
You are removing the part of the cluster.
Okay, if I understand correctly, you mean where is it?
That block.
This one before?
Yeah. That, yeah.
Okay, okay, well, this one.
Yeah.
So sorry, say it again. So I'm getting a high temperature.
You are getting too low luminosity because you remove the central part of the cluster. So you don't measure the core of the cluster.
Okay.
So you underestimate the luminosity.
Okay.
Or the temperature is biased because again you don't account for the central part of the cluster,
Which could be the coolest part.
Exactly.
Okay. Well, in this analysis, I removed only the two central arc seconds, which usually are used to remove points like sources, but if they are at high redshift,
exactly. Depends what is the physical scale.
yes. That's a good point. That's a good point that the referee didn't raise. Okay, so probably I will add it to the discussion. Thanks.
Okay. And then if I can ask the
Can I follow up 1 second about this actually, because I have a question also regarding this. So I see that your extended emission around the nuclear part is kind of, it's limited, it's not that much extended, right?
No.
So how sure you are that this temperature you're measuring here, they are hint of this extended X-ray emission and not, they are not associated with something like the accreting flow around this BLR. So something like
No, but those are radio galaxies. These are radio galaxies.
Okay.
I didn't do this for the Blazars. For the Blazars, I just measure them. I didn't compare it. You mean probably this?
Yes, exactly.
Okay.
So this you don't try to compare with
No,
temperature in cluster or group.
I did not. As I told you, what I did was to exclude the central region up to where the PSF contribution was smaller than 1%. So beyond this point, the contribution from the PSF that we get from the 50 is smaller than 1%. But as you said, there could be other factors like where we don't mention accretion.
Yeah, I'm thinking if this can give you an idea about the temperature of the accreting flow, something like within a bond radius.
I think
or the resolution is not enough.
No, I don't think. No, the boundary radius is way smaller than that. Also, you can probably resolve it with subpixel techniques, but you need a much longer exposure than this one. These are bright sources, so in order to reduce pileup, they are performed for shorter time or within sub-array mode. So we don't get all the counts that we need to go down with the resolution. The pixel size in the 0.5 seconds. So we probably cannot see down the boundary radius.
Sorry.
You have another question?
Yeah, the question was about the WISE classification for the
WISE classification.
So
Why this one or the original one?
Either of the two. So my question is, how were the original blazars that were used to identify the locus of the blazars were selected?
They were selected from the pizzicat. And the pizzicat, cross-matching the pizzicat with the Fermi catalog.
Okay.
So all the pizzicat are identified and selected one by one by hand, looking in the literature and finding published spectra. So it may be incomplete, but it's very pure. Because all the sources are classified on the basis of published, not just someone saying we look at the spectrum. There must be a picture of the spectrum, okay, and it's rechecked and everything. So all the sources used to define the wise locus are for sure pleasant. Probably we're missing something. Sure, yeah, okay. And of course, they must have gamma ray emission. There is also a version of this without the gamma ray emission, but it's much less concentrated.
Exactly. Okay.
So this is the spine, let's say, of a little bit broader. Let's say if this is the Blazar gamma ray Blazar locus, the whole Blazar locus is something like this, a little bit more spread and less concentrated. Okay.
Yeah. Yes.
So these sources are the sources that you use to produce the KD method?
Yes.
Okay, so given that you trust all these sources, that means that although that the number of resources is low, you trust the KD because KD is sensitive on the number of,
yes.
Of the points that you have in order to describe the parent distribution of the channel.
Mm-hmm.
So although that the number is low here, you trust the KD method. I do,
first of all, because there is not something much better that can be done, because Blazars are not a lot, and the BZGAT list something like 3,600 sources. They are not a lot, I agree with you, but this is the best that you can do. Another way, another reason why I do trust the KDE is that, especially for BLX, for spectral radio waves are not that much, but for BLX, the locus in both wise projection, it's very well separated from the stake, the bulk of the wise background sources. They are not BLX. So there is a fair separation between BLX and the other wise sources. So we are quite confident that if a source falls there, it's most likely a BLX. Not so much for spectral radio waves because they overlap a little bit with QSO, with Blazars that lies here. And so there is a little bit of overlap over there. I give you that. But for BLX, the selection is pretty robust and has been confirmed in subsequent releases of the Fermi catalog, in which a lot of the sources selected like this turned out to be Blazars.
Okay, so if there are no more questions, then thanks, Alessandro, again.
Thank you.